All right, now that I got you guys all riled up, let's cover new material. Yeah, we're going to finish up chapter 1 today and then go into chapter 2. And some of you were asking me about this because it was on sapling. And the last section in chapter 1 is the solubility of organic compounds. There's only a couple simple rules you need to know. You guys already covered solubility for inorganic salts in general chemistry, right? You guys remember about cuprates and nitrates and things like that. We're not going to cover solubility of salts. We're going to cover solubility of organic molecules. And for organic molecules, the rule is very simple. And the easiest way to remember this is that like dissolves like. What the heck does that mean? If I say like dissolves like. Yeah, the more similar they are, meaning they've got similar intermolecular forces, that means they tend to dissolve one another. So let's take a look at an example of oil, which can be represented as CXHY. So it's a hydrocarbon with varying amounts of carbon and hydrogen coming off of it, and water, which is just good old-fashioned H2O. What's the main intermolecular force for oil on the left? It's nonpolar, so it's London dispersion, right? So the main intermolecular force here is London dispersion. And water is going to be what? H bonding, right? Or hydrogen bonding. And we can also say there is 25% London dispersion within water. But are these very similar? No, water is very, very polar. Oil is very, very nonpolar. So any of you that have seen an oil slick on top of a lake or in the Gulf of Mexico, you've seen very clearly that these two will not mix very well. So this is our rule of thumb for organic molecules. You have to have similar solvents, meaning that bulk liquid, in order to dissolve a solute, right? So if your solute has similar chemical properties to your solvent, they tend to be miscible, meaning they'll mix evenly. There's also a rule for organic and cation or anion interactions. So let's include this. So for ionic or charged molecules, or atoms, they dissolve more readily in solvents that can hydrogen bond. The classic example of this is ocean water, right? So if we look at seawater, we've got sodium chloride and a bunch of other salts dissolved in there, but they stay in solution. And the reason for this is you can imagine, let's say we've got a water molecule here, and it's got its lone pairs, and we've got a cation floating around in solution. And I'm just going to show that with a positive charge. The oxygen will actually stabilize this cation because it has a lot of electron density on it, right? So we said that oxygen's got a net dipole pointing in its direction. That means it's got a delta negative. That delta negative on the oxygen will stabilize that cation, which means water is a really good solvent for salts. Conversely, if we think about our anion over here, the anion is going to be attracted to a completely different part of this molecule. And all of these are due to the delta positive and delta negative portions of our water molecule, right? So salts are really good, or they're very soluble in solvents that can H bond, for the most part. In organic chemistry, you guys will learn there's exceptions to just about every single rule. Salts are one of these. There are some salts that will not dissolve in solvents that can H bond, and you guys covered that a lot in Gen Chem already. There's a really cool example of solubility that I wanted to talk about.
So are you saying that the negative oxygen is attracted to the positive?
Yeah, so if we think about the oxygen up here, it's got a delta negative, delta negative, delta negative, right? All of those delta negatives will stabilize that cation because they're really rich in electrons right now. But if we look at the hydrogens over here, these hydrogens are delta positive, which will stabilize an anion. So we end up with salts that are being stabilized by partial positive charges on the water molecule or partial negative charges.
Oh, there's a cation plus anion.
Yep, exactly. You want opposite charges to stabilize. There is one really weird example. Soap. Soap is one of my favorite compounds to talk about. And I'm going to put a little X down here indicating that the soap identity can vary by some numerator or some multiplier. And if we look at soap, soap will dissolve in really polar solvents or really nonpolar solvents. And why is that? It's amphiphilic, right? It's attracted to both water and oil. But why? What do you think?
Well, it's got a tail, a hydrocarbon tail, but it's got a polar, I guess, head come off. It kind of looks like a lipid.
Okay, so this side's nonpolar. This side over here is polar. So if you actually look at soap in solution, it does something neat. So I'm going to draw a little oil droplet in solution here with this squiggly oil, right? And I'm just going to abbreviate this using my wonderful artistry skills here. The cool thing with oil is that these nonpolar tails can actually wrap up oil droplets. And then on the outside here with these charged oxygens, they're really attracted to water. And so soap can act as this emulsifying agent where it can actually hold oil into water. This is becoming a really big deal for a lot of different reasons. One is drugs. So if you think about drug development, a lot of the drugs that we ingest are very nonpolar. How do you get them to go into something that's primarily water, meaning you? Oftentimes you actually have to encapsulate them. And so this is a big part of the pharmaceutical industry now. It's also big with environmental remediation. So how many of you guys saw the news about the Deepwater Horizon spill a couple years ago? You guys hear about the chemical dispersants that they were using? So essentially they were flying these giant tanker jets above the oil spill and spraying down soap, more or less. And the idea is that the soap would trap these oil particles and essentially cause them to mix with the ocean. The more they mix, the easier it is to break them down by the little microbes in the ocean. But there is a lot of questions remaining about whether or not that was the greatest idea, because we're sending down submersibles and finding these giant soapy oil slicks on the bottom of our ocean floors. So it's a changing industry, but it's a really important industry. We're going to actually be making soap later on this year, so if you hang on through term 3, we get to make our own soap, and it's a pretty neat lab. But this is kind of a unique property where some molecules are amphiphilic. Amphiphilic, meaning they dissolve in oil or water. They don't really have a strong preference towards either one. All right, so we're going to change gears to chapter 2. Hopefully you guys had a chance to work on a lot of your sapling problems over the weekend. Chapter 2 is really getting into the heart of organic chemistry here. So chapter 2, the first thing we're going to talk about is molecular representations. And this is something that chemists don't always agree upon. Oftentimes people have different ways of representing the exact same molecules. And let's talk about the different ways we can represent a molecule. The first one is just with molecular formulas. So let's say I've got a molecule, it's C3H8O. That's one way of describing this molecule, right? Let me clean up that 8. But what's a downside to a molecular formula? Yeah, we don't know the actual layout of the carbon atoms. Is it branched? Is it linear? What's going on here? It gives you no information on connectivity. I really don't like seeing organic chemists working with molecular formulas. It doesn't tell you enough about the molecule. There's another one that's a little bit better, but still not my favorite. And this is the condensed structure. The condensed structure, what we do is we try to lump similar groups together. So in this case, we've got 2 CH3 groups, so we put a bracket around them and put a 2. And then we've got a CH and OH. And what this does is it gives you a rough idea of connectivity by grouping similarities. All right, and then there's an additional one that is partially condensed. Oops. And a partially condensed structure gives you more information. And this is what I tend to use because it shows all of the individual bonds between important atoms, but we still group some of the similarities, so it's a little bit faster. So the nice thing with this is you can abbreviate groups. And it shows connectivity. Normally in this class I'm going to use the partially condensed structure because it's a lot quicker. But the one caveat is we will be taking an exam later in the year where the exam format is done in the condensed structure. So we need to know how to be able to flip back and forth between the two types of structures. You can see on the condensed structure it says CH32. That means we've got these 2 CH3 groups, the one on the left, the one on the right. Then we've got the CH right here, and then the OH. So it gives you an idea, but it does take some practice interpreting what each of these mean. There's also a few time-saving techniques we can use for partially condensed structures. And some of you may have already seen these before, but let's go through them. All right, the first time-saving technique is that all termini or vertices are assumed to be carbons unless otherwise specified. Are assumed unless otherwise labeled. So this saves us a lot of time. The other thing that saves us a lot of time is just omitting hydrogens. If we don't draw hydrogen, you can assume there's hydrogens there. So all CH bonds are assumed. But not drawn. The last one is that lone pairs are assumed. But I'm going to put an asterisk next to this. And the reason I'm putting the asterisk down is I want you guys to keep on drawing lone pairs for quite a while, because it does get confusing unless you include them. It can be hard to know what the charge is on an atom unless you know how many lone pairs there are. So for right now, we should continue drawing all lone pairs. But let's take an example of this. And the example I have is this molecule. How many hydrogens are in there? Or sorry, how many carbons? Three, right? So the termini, we've got two different termini, and then we've got a vertice right there. Each of those represents a carbon. So we go carbon, 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 double bond to an oxygen. The oxygen, because it's not labeled as being charged, must have two lone pairs. And are we done? No, we also have some hydrogens coming off. So because we haven't included all of these hydrogens, we can draw them in. And you can see it took me a lot less time to draw the molecule on the left than it did to draw the molecule on the right. So anytime you see a termini from a single bond, it's going to be a CH3. Anytime you see an oxygen without lone pairs, you can assume there are lone pairs unless there's a positive or negative charge on it. So this is a really nice way of speeding up drawing. One last thing I wanted to hit before we head out today is up here I was saying that we group similarities on organic molecules, right? What we call these similarities are functional groups. How many of you guys have heard the term functional group before? Yeah, so you guys have covered this a little bit in general chemistry. And functional groups are kind of like the body parts of organic chemists, or organic molecules, not of organic chemists. But what I did for you guys, it's been one of those days. If you go on the class website, this doesn't look very good. It's pulling up the... Yeah, here we go. So if you go under class handouts and you go to functional group flashcards, you can pull up Quizlet. How many of you guys have used Quizlet? It's like online flashcards. What you can do is either use flashcard mode, learn mode, speller mode if you struggle with spelling like myself. You can do test mode, or you can do a race game or scatter game. And this is a really good way to learn functional groups. I told you guys I really hate memorization. I'm not a huge fan of it, but we have to know these names. It's like learning a language. We have to learn some of the core vocabulary. So use this with your problem of the day. And then on the back, try to find at least 5 different functional groups in that crazy looking molecule, and then circle them and identify them.